Here we go. All right. So we're covering general topics of bonding in these, in Chapter 8 and the beginning of Chapter 9. Let's see. I don't think I owed anything else. I returned all the ones I had. Anybody have molecular weight of an acid? Or are you going to turn it in online? Because that was due today. Yeah. Okay. You look sick.
Nah, just sciences.
Oh, okay. All right. So, review document. Anything in the review document that get in trouble? Oh, yeah. So I've already got one there. Find it. There it is. That's the name. Okay. Anything bothering you? Four weeks to go. Just in case you're interested.
Not too bad.
Want to do like we usually do? I'll just start off and something will pop into your head. Okay. So, the first one just says the force between two bodies have identical electric charges. Okay. So we're looking for A through E. Which one of these describes that force? The force between two bodies having identical electric charges. A says it's a force of repulsion. A force of repulsion. Is that true? That's A. Yeah, they're identical charges, so that one's true. B says force of repulsion if the charges are negative, one of attraction if they're positive. No, oh, that's kind of crazy. C says increases as the bodies are moved further apart. Increases with, and I think that the variable is R for distance. That's false. It decreases with distance the farther apart they get. That force is independent of the distance between them. Independent of R. That's false. Is directly proportional to the distance between them. Directly proportional to R. What would that mean? If it were directly proportional to R, the force would increase as R increases. Right? They lockstep, they both increase. That's directly proportional. That's the same as C. It can't be right. They're inversely proportional. So the bigger R gets, the smaller F gets. Yeah. Okay? Okay, 2. So if atoms have equal or nearly equal electronegativities, so if you have 2 atoms with equal electronegativities, En, what should you expect? A no bond? That's false. Because we do have molecules of 2 identical atoms. All the diatomics are that way. H2, N2, O2, F2. So that was false. Polar covalent bonds. Covalent bonds. The covalent's true, right? How about that? If they're nearly equal in electronegativities, then they're not going to be polar. They're going to be non-polar. And that's C. Non-polar covalent bonds. C is correct. D is ionic. What do you need to have an ionic bond? We didn't talk about specific values, but the difference in electronegativity determines whether it has a largely ionic character or largely covalent character. Right? So when this one gets really big, you can have an ionic bond. And you'll see that with one atom is from the left-hand side of the periodic table, and the other one's from the right-hand side. They need to be widely spaced to give you an ionic bond. So this condition is not conducive to ionic. And E, well, covalent bond. That's true, but it's not the best answer. Right? That's why I always put up at the top of your test, choose the best answer when in doubt. Because this one is true, but this one is truer. Right? So they're both good, but this one's better. Come up with anything yet? Okay. How about this one? We've got cesium, fluorine, and chlorine. And you want to put them in order of increasing electronegativity. So the electronegativity needs to increase from left to right. So which is the least electronegative and which was the greatest electronegative? Greatest is easy. Fluorine. So fluorine is the greatest. How about chlorine? What's its relationship to fluorine or cesium? Well, chlorine is just a little bit less electronegative than fluorine because it's right below it. So it'll be here. And cesium is way over on the left-hand side of the lower left corner. So it's going to be the least. It's going to be way over here. So let's see, that one is B. That's B.
What about 13?
13, all right. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure whose skeleton is this one? Okay, so this is what we're given. And the carbons are numbered, so we can tell them apart. And then you have okay. Right, this is the skeleton. This is not the Lewis dot structure yet. Okay, So how do we draw the Lewis dot structure? You take the valence electrons for all the atoms and add them together first. So that's 1, 2, 3, 4 times 4 is 16. 1, 2, 3, 4, 5, 6 hydrogens. And oxygen should be 6, I think. Yeah. Okay. So 12 and 16 is 28, right? 28 electrons. Then you take the electrons and you make a bond. And that's the reason they gave us this skeleton, because if you ever get into organic chemistry, you'll find out that there are just thousands of different possibilities. The more carbons you get in there, the more possible arrangements you can have. So they gave us the basic structure to head us in the right direction. Right. So we've got our 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We used 20 electrons. So we got 8 left. So the next step is, after you've set your bonds, the single bonds, then you take these 8 electrons and you start from the outside working your way in. Okay? We can't put any more on hydrogen. It can only take 2. It's already got 2. Right. So the next place to start would be oxygen. So with 8 electrons, we can put 2, 4, 6. Put 6 more here. So we've got 2 electrons that need to go somewhere. The, well, let's see. 2, 4, 6 for that carbon, 2, 4, 6 for that carbon, 2, 4, 6 for that carbon. Right? So we could just move in here and put 2 right there. And where's the best place for them to go? Well, you may not know this, but they tend to go toward the more electronegative atom. Right? So these would go here. Right? To give you, because we've got 2, 4, 6, 8. Well, we got 2, 4, 6, 8 there. That logic doesn't work, does it? Because we could say that, couldn't we? 2, 4, 6, 8. Okay. Let's see what the question is. We may not have to go that far. How many electrons must be shown as bonding or non-bonding electrons in the Lewis structure? Oh, I'm making this harder than it needs to be. Why didn't you say something? There. That's the answer. Bonding and non-bonding together is 28. That's the question here, is just to see, can you add up all the valence electrons? Right? We need more information to complete that structure. Just for your information, this is probably true here, and then this would be over here. So that would give 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That's probably what it is. But that doesn't, you don't need to know that to answer the question. You just need to be able to count the valence electrons. My students are very consistent. It doesn't matter what class I'm in. If I start going off doing something extra or wrong, I just sit back and watch them. It must be entertaining. Oh, the next one is using the same structure. How many electrons are shared between carbons 2 and 3? And they give you the name of the molecule. I don't think we've covered, I don't think we're able to do that one. I just told you what was between 2 and 3. It's a double bond. So that would be 4 electrons. So I'm thinking that if this one shows up on the exam, I better just give it to you. Right? Because I don't think we've covered enough material. to actually know that that double bond should go there.
So the answer is 4.
Yes, it's C for number 14. Number 14 is C. One more?
So number 15 also talks about double bonds.
Oh, okay. Which of the following molecules contains a double bond? This might be doable. Okay, so let's take 15. We have to do each one in turn. So carbon dioxide should have 4 from carbon and 2 times 6 or 12. That means 16 electrons total. Let's do that first. Let's just add up the electrons. So nitrogen is 5. Yeah. 5 and 3 is 8. So these are the total electrons for each one. Water is 6 and 2 is 8. And then D is all, and E is none. Okay, so if we got 16 electrons, carbon's going to be in the center. Right? So that's -4, which makes 12 electrons. So we can start going from the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All the electrons placed. But carbon needs 1, 2, 2, 4, 6, 8. It needs 4 more electrons. So we can take those 2, and we can take these 2. And that would make now we could just as easily have taken 2 pairs, right? Made a triple bond here, right? But how do we know that that's not the best one? Formal charge. If you calculate the formal charge on this one, oxygen has 6 valence electrons, and it's given 2, 4, 5, 6. -6, 0. That's good. If we did a triple bond here, it would be 6 minus 1, 2, 3, 4, 5, 6, 7. Be -1, right? That's less desirable. So both of these oxygens have a formal charge of 0 if you have a double bond on either side of the carbon. But if you have a single bond on one side and a double bond on the other side, I mean triple bond over here, this one is -1 and that one's going to be +1. Because you would have 1, 2, 3, 4, 5, 6, 7. Well, no, that makes, what am I doing? 1, 2, 3, 4, 5, 6, 7. This is -1. Formal charge. Triple bond would be 1, 2, 3, 4, 5, 6. No. Sorry, triple. 1, 2, 3, 4, 5. +1. Sorry. I forgot that this one goes over here to the triple bond. Make a triple bond. So this side would be +1 and that side would be -1. If we had a single bond here and a triple bond there, and the formal charges, you want to minimize them. You want to get them as close to 0 as possible. And double bond on both sides makes that happen. Now the Lewis dot structure of a single triple is a valid structure. It's just not the best one. Okay. So let's go back to the question. Which of the following molecules contains a double bond? Well, that one contains a double bond. In fact, it contains two of them. Let's see if we got double bonds on any of the others. Okay? Okay, so that one is the best structure for that. How about ammonia? So it's going to be like this, 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 this. 2, 4, 6. So we got 2 more electrons to go somewhere. Can't put them on any of the hydrogens. Has to go on the nitrogen. And in that case, we don't need a double bond. We can't make a double bond because hydrogen can't take anymore. Right? So that one doesn't have a double bond. How about water? Oxygen, hydrogen, hydrogen. Okay, so that's 2, 4. We got 4 more electrons to go. Can't put any on hydrogen, so we got to put them on oxygen. I know that's not the structure, the shape, but for a Lewis dot structure, it's good enough. We can't make any double bonds here because it's all hydrogens, right? Okay, so that one won't work. So it's not this one, and it's not that one, it's this one. That's the only one that has double bonds out there. Okay. Ooh, we talked about resonance, didn't we? When you have more than one possible Lewis dot structures and they're equally valid, in other words, their formal charges are virtually the same, but you have more than one structure, then the way the localized electron model deals with that is through resonance. You're right, both or all structures, there could be 3 or 4, and you put that between them. It says they resonate back and forth among those various structures. You have to do it that way because the localized electron model says electrons belong to atoms. Right? You can't spread them out. They have to be assigned either in the bond or in lone pairs. Right? So that's why the localized electron model has the resonance as a fix. It's not the best fix, but it's the best that that theory can do. It isn't until we get to molecular orbitals that you can just throw the whole thing out and start over again. We won't talk about that until next time, next exam. So why am I talking about that? Number 18. Which of the following exhibits resonance? Okay, we've got ammonia. It only has one possible structure. That's it. Can't make any others. Right, so no resonance there. PCl5. We haven't done that one yet. So this is 7 for chlorine, that's 35, and 5 for phosphorus, it's 40. We've got 40 electrons here. So P there, 1, 2, 3, 4, 5 chlorines. So that's 2, 4, 6, 8, 10. So we need 30 electrons. So it's 1, 2, 3, 4, 5, and we got room for 6 in each. Right, so that uses them all up. Is there any reason to draw any different structures than that? Probably not, because what's the formal charge on chlorines? Well, they got 7 electrons, valence electrons, and in this structure they have 1, 2, 3, 4, 5, 6, 7. So each chlorine has a 0 formal charge. How about phosphorus? It's got 1, 2, 3, 4, 5, and it has 5 valence electrons when it's not bonded. So it has a formal charge of 0. That's the best one. We can't draw any better. How about C? Oh, that's water. All right. So we know water's like this, and it only has one possible. Right. Can't draw any differently than that. How about T? Ozone. Okay. So oxygen's going to have 6 of 18 total, and going to be like that. 2, 4 means 14. So we start from the outside, work our way in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is that right? 2, 4, 6, 8, 12. That's 12. So we have 2 more. Where do they go? Well, we have to put them here. Right? That has an octet, that has an octet, this one doesn't. Right? So how are we going to get an octet out of here? We can't steal those 2 electrons, because if we make a bond out of those, we're still short. So we have to take one of these pairs, put it over there. And that makes, right? Still have a lone pair there, and we have this one, and then only 2 pair over here. Okay? But who's to say we have to take that one? Couldn't we take one pair over here? Right? We take that pair over here, that puts the double bond on the other side. Now we have equivalent Lewis dot structures, and the only way to resolve that is resonance. So, let's see, where was I? At least 2 of the molecules exhibit resonance. No. So E is wrong also. This is the one, the only one that satisfies conditions. Ozone. Okay? Well, let's see. 19 is a corollary to that. If you did 18, you know the answer to 19 is B. 2 possible structures. How about 20? Which of the following types of molecules always has a dipole moment? First of all, what do you have to consider to find out if a molecule has a dipole moment? 2 things. Do the bonds have dipoles? And what's the geometry? Those 2 conditions. So A is a linear molecule with 2 identical bonds. If the bonds are identical and it's linear, it doesn't matter if they're polar or nonpolar, because the identical polarity of the bonds will, well, let's see, will cancel each other out. That's not worded very well. Okay, I get its meaning. If we have something like carbon dioxide, that bond is identical to this one, right? And it's linear, so those 2 dipoles cancel out. So A can't be it. How about B? A tetrahedral molecule. 4 identical bonds. For the same reason. Those bonds, well, these bonds don't have to be polar, but if they are polar, they're still going to cancel out. Same for here. If these bonds are polar, then they're pointing to the apex. What's the plural of apex? Apices. pointing to all the corners of the tetrahedron. They're equally spaced and they cancel one another out. So neither one of these will produce a dipole moment. How about a trigonal pyramid molecule? Trigonal pyramid with 3 identical bonds. What does that mean? What's a trigonal pyramid? Well, if you have one here, and you have one there, one in the back, one here, there's your trigonal, and there's your pyramid. Right? So it doesn't matter if this has a lone pair up here. A lot of them do. But if this is a dipole, let's say Y is the more electronegative. Then it goes like that, like that. They're all pointed this way. So we put them all together, and you get a summation of a dipole in that direction. That will always be a polar molecule. So C satisfies the conditions. How about a trigonal planar? So what do you have there? Well, looking from above, you have, let's see if I can think of one. How about this one? Boron trifluoride. It's going to be boron in the middle, fluorine, 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 like that. So there's your trigonal, and they're all in the same plane, doing that. They cancel one another out. So that one is nonpolar also. By the way, that one is deficient in an octet. It's less than an octet. But it's real. So we just got to deal with it. Did I miss any? None has a dipole. Well, E's false. So C is the answer to 20. This chapter mostly concepts. Doesn't have a lot of calculations, does it? Oh, there's a calculation, lattice energy. Calculations involving lattice energy and bond energies. Okay, so we have a little calculation. Not a lot. Number 24, I didn't give you any guidelines for that. Difference between, how do you tell ionic from polar covalent? No. It varies from author to author, but if you've got, let me think, a difference in electronegativity of, I think it's less than 0.5, you have nonpolar. And then it'd be greater than, let's see, between 0.5 and 2, I think it's 2, you have polar covalent. That could be 0.7, I'm losing my mind. And then greater than 2 is ionic. I think I've seen that quoted. So if you have the electronegativities, you can determine what the difference is. But we don't have those for number 24. Which of the following bonds would be most polar without being considered ionic? Right, so here are our choices. And these are just bonds. These are not the molecules, right? So we're not trying to balance charges. D is silicon and oxygen, and E is nitrogen and oxygen. Okay. So let's see. What the question says is most polar without being ionic. Right? Which ones in here are ionic? Definitely magnesium and oxygen, because they're on opposite sides of the periodic table. So this one's ionic. Right? That one's covalent, but it's nonpolar, right? That's nonpolar, because they're equal. So we can get rid of this one and this one right off the bat. Then we look at the difference between their positions on the chart. Since they're all bonded to oxygen, then we just have to say which one's farthest away from oxygen now, right? Carbon is 2 steps to the left. Nitrogen is 1 step. So this one is more polar. How about silicon and oxygen? Well, silicon is to the left 2 steps and down 1 step. So this one has to be. It's not far enough apart to be ionic. Right? So this one has to be the most polar. I think that's the answer given. Yeah, D. So what that means, probably that sand, beach sand, is a covalent compound. Never thought of it that way. It's very polar covalent. Okay. In my hand. Well, you know, I forgot to put the 1 in there. Just created a new course. It's 2 blank 3. Speaking of creating new stuff, you see in the news where Kirsten Gillibrand is one of the myriad Democrats running for president. Kirsten Gillibrand was in a town hall thing. She invented a new class of nuclear weapons. They're called tactile nuclear weapons. Did you see that? I think she was trying to say tactical.
Oh.
We call them tactile nuclear weapons. Okay. Those are the ones that you can touch. Okay. Enough ridicule for one day. Let's move on. Let's see. Oh, okay. 26. We talked about electron affinity already in a different chapter, haven't we? right, since I started this conversation, I might as well finish it. So the first electron affinity value for oxygen is blank, and the second affinity is blank. Exothermic versus endothermic versus favorable, unfavorable. Electron affinity. Okay, how do we define electron affinity? We start with the gaseous atom. And then you allow an electron to associate with it, which produces a gaseous anion. Right? So that's the first electron affinity, EF1. Is this going to be endothermic or exothermic? When an electron comes close to, it comes from infinity down to some lower orbital next to an atom, it always gives up energy. So this is going to be exothermic and favorable. The second electron affinity would take that gas and see if we can associate another electron with it. This is EF2. Analogous to ionization energies, first and second. So, how are we going to get this electron, negative charge, to associate with that oxygen, negative charge? We're going to have to force it, right? We're going to have to add energy to make it go there. Right? So that one is endothermic. It does not want to be there as much as this one does. So that's endothermic and unfavorable. But that begs the question, because we know when we're assigning charge to oxygen in a molecule and starting to do our balances, we always say oxygen's 2-, right? So if it prefers 2-, there has to be a reason for it, right? So one way to look at it is, if we combine these two equations so that we have that plus these two electrons and that one cancels and leaves us this, then we add these energies. If this one is more exothermic than this one is endothermic, then the summation of the two makes it favorable. Okay, that's one way to look at it. The other way to look at it is electron configurations. Right. So oxygen is going to be 2s2, 2p4. 2s2, 2p4. And that's the valence shell. We do the complete, and that is 2, 4, 8. Right, 8 total electrons. So we know p orbitals can hold 6 electrons, and that's their preferred state, because at this point you've got like that. If we can put 2 electrons in there, then let's see, plus 2 electrons, what will it look like? 1s2, 2s2, 2p6, which is neon. It looks like neon, right? And that's another way to think of it. Completing the octet is a desirable reaction to satisfy unfilled orbitals. Right? So that's another way to rationalize why oxygen would have 2- if this one's favorable and that one's unfavorable. see how we're doing on time, because we got a lab today. 2 o'clock. And, 3:45. We're probably not going to need all that time. This is an easy lab. I always say that, don't I? There's some calculation. Use the following reaction data to calculate the energy of an HF bond. Can I do that? See how I presented it. Okay. Do we want to do that? 27. Use that data to calculate. That looks like a bonus question to me.
Let's do it.
Okay. Got nothing to lose, right? This is not an exam after all. Okay, so we have, if we want to calculate the energy of an HF bond, let's define our target equation first. What would give us the energy of an HF bond? The energy of an HF bond is the energy required to break the bond. Right? So if we start, let's see. I don't want to get down this road and realize that I'm talking out of both sides of my mouth. Yeah, okay, that's where I was going. So our target equation is this one, which is that bond, right? And we want to break that bond into individual gas atoms. Right? So we want to know what's the energy required to break that bond. So it'll be an endothermic process. So we should see this value as positive. Okay. So now we've got these three equations. H2 gas plus F2 gas yields 2HF. So that gives us this side of the molecule, if we use that. So H2 gas plus F2 gas yields 2HF gas. And that is minus 542 kilojoules. Okay, we need HF on this side, plus we need only half of it, right? So if we flip it and take half of it, we should get HF gas. Let's see. Let's do it this way first, like that. Yields this one plus this one. And then we're going to take half of that. Okay? So that makes this one positive first, and then half of that. So that'd be 271 plus 271 kilojoules. So that gives us this part here. Now, how about this one? What's the next one? H2 gas yields 2H. So that puts H on that side. That's where we want it. H2 gas yields 2H gas. And that's plus 432. So that one's going to be the same sign because we're not going to flip it. But we do need to take half of it to give us that value. So we say, let's see, took half to get down here, so that's good. Here we want half of that. So that gives us 1/2 H2 yields H. And this would be half of that. be 216. Okay, so we're going to use this one. I didn't finish writing this one out correctly, but we're going to use it anyway. And then the last one is F2, like this one is. Yields 2F gas, and that's 154 kilojoules. Yeah, they're all kilojoules. So we need half of this one to give us just one of those. 1/2. So this one will be 1/2 F2 yields F, and then this value would be 77. Did I hear 77 back? I gotta check every now and then so it's not some voice and I'm hearing your voices. Okay, so these are the three we have to add together. All right, this is going to be 1 HF. We keep that one. This is going to be 1 H2. But that's only a half H2. Oh, that's a half, right? If we get rid of that, so that's 1 HF. This is a half. This is a half. Right. I'll let that part out. Sorry. So now, keep that one. This one cancels, and this one cancels. Okay? And we keep this one and this one for these two. Okay? So we're good there. You got what we need. We need to add. This one's already been done. So we add that one to this one and to this one. So 271, looks like we're going to be endothermic. And 216. 564?
I did in my head, but yeah, I can probably use 560.
8. 5. Yeah, you have to carry the 1. Yeah, 564. Now, is that right? Does that agree with the answer? Yep. That's what that says. Did I lose anybody? We're good? Okay. We just use Hess's law is all. That dry out. Okay. Okay. Do I have trouble with 29? Which of the following contains a carbon atom with trigonal planar geometry? If I didn't drive that point home, these geometries that we developed from the localized electron model and VSEPR, which is part of that model, are assigned to individual atoms. So you can have several different types of geometry within the same molecule. Now, if you have a molecule that only has one central atom, of course, the whole molecule has that geometry. But if you have molecules with multiple centers of geometry, then they can be different. They can be the same, or they can be different. So, which one of these has a trigonal planar geometry as a carbon atom? Okay, first one. CH3CHO. CH3CHO. Now, we didn't go over this before, but when you see something like this, this is organic chemistry convention in the way we write compounds. This carbon is bound to that carbon. Okay? Then these hydrogens are bound to that carbon. Okay? And this hydrogen and that oxygen are bound to this. Like that. That's not finished yet, but that's the framework. Okay? So if we look at the way it's written here, this carbon's already got an octet. That carbon doesn't have an octet. So we need to assign a Lewis structure. So we got 2 4s is 8, and 4 hydrogens and 6 oxygens. So that's 18. We got 2, 4, 6, 8, 10, 12. So that's 6. 2, 4, 6, yep. 12, yep, 6. So we got 6. We can do here, 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 here. And all we have to do to satisfy that carbon and this oxygen at the same time is move that over here. So that gives us like that. Okay. So what's the geometry for this one? Carbon has 4 groups around it. It's tetrahedral, right? How about this one? 1, 2, 3 around that carbon. That's trigonal planar. Wasn't that the question? Yeah, trigonal planar. So that satisfies the conditions. And if you're in a hurry taking a test, that answer works. It's not none of these, so mark it down and go. We already know carbon dioxide is linear. Right? CH3Cl, which is methyl chloride, chloromethane. And C2H6 is another organic compound that we haven't named yet. It's ethane. But it's going to look like these 2 carbons and hydrogens all around it. So that has 4, that has 4. They're both tetrahedral. This is the only one that has a trigonal planar. Okay? So you got some organic chemistry for free. Let's see. I want to be sure we make it to the end. We'll come back to those in a minute. Let's see. Yeah. Let's go to the short answer questions for now. Then we can go back to the other stuff. So 53 says, in spite of the large electronegativity differences between bonded atoms in beryllium chloride. Yeah, that would be true. Beryllium's over there, chlorine's over here. beryllium chloride has no dipole, while sulfur dichloride does have a dipole. What's the explanation? Well, let's see, here's beryllium chloride, or dichloride, and here's sulfur dichloride. So we need, let's see, no dipole here. You're given that because we can measure it. And this one does have a dipole. We have to explain why. Okay, Lewis dot structure. 2 times 7 is 14, and beryllium is 2. So that's 16. 16 electrons. So we have beryllium in the middle, and chlorine. That's 2, 4. So 12 electrons. 2, 4, 6, 8, 10, 12. So even though we have this, beryllium is deficient. It's octet deficient. But it still has 2 groups, so that means it's linear. So this is true as written. These dipoles cancel one another out. That's why beryllium chloride has no dipole. Why does sulfur dichloride have a dipole? Well, sulfur has 6, and 2 chlorines is 14, so that's 20. Okay? So sulfur, like that, that's 4, equals 16. So we have 2, 4, 6, 8, 10, 12. That means we have 4 electrons left over. They have to go on the sulfur. Okay? So now, sulfur has 4 groups around it, which means tetrahedron, but that's an electronic tetrahedron. So we have sulfur in the middle, and then we have, let's see, we'll put 1 chlorine up here, 1 chlorine down here. That means this one, like that, and this one is in the back to make our tetrahedron. So now what's the molecular structure? Because the dipole is this way and this way, right? Let's see, let me draw it this way. There you go. So chlorine is more electronegative than sulfur, but you still have those 2 lone pairs. The idea is that these 2 add up to something here, and the question is this dipole enough to overcome those 2 lone pairs on that end? Probably not. It's probably negative that way. But the point is, the vector sum gives it a dipole. Right? It's not linear, it's not regular shape. The dipoles cannot cancel each other out. That's why this one has a dipole. So you got 1, 2, 3, 4, 5, 6, 7, 8. You got 8 lines. Yeah. You can write big and still get all that in. Okay, that's 53. Let's look at 54. And then we can go back to anything else you want to look at. I wanted to get these in for sure. Okay. We have this compound. Okay. A says draw the Lewis dot structure. All right. So 7, and each of these is 7, so 5 times 7 is 35, right? Plus 1. 36, because that one counts too. So we have 36 electrons. Iodine's in the middle. We have chlorine, 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 chlorine. 2, 4, 6, 8. 28? Yeah. So 2, 6. 6 times 4 is 24. That takes care of those electrons. Now, where do those 4 electrons go? Got to put them on iodine. So iodine is going to exceed its octet. Got 2 here. You're there. So we have 6 groups, right? What does 6 groups mean for electronic structure? I hear the voices again.
Is it octahedral?
Yeah, octahedral. So that's. Now, in order to draw the, well, that is the Lewis structure, except for one thing. It has a charge. It doesn't say where the charge comes from here, but it does have a charge. So you need that also. Then we need to get the shape of the molecule. So that's B. That was A. This is B. What's the shape of the molecule? The question is, where do those lone pairs go? They want to go as far away from each other as possible, right? So the octahedron is like that with iodine in the middle. Like that. And you could put chlorines up here, then you'd have to put lone pairs down here. And if you did that, that would give you kind of a lopsided picture. The best place for lone pair electrons to put them as far away as possible is these 2 apex. Now, true, we could put them here and here because this is 180 degrees, right? But so is this. That would be 180 degrees then also. Right? But if we did that, then we would have chlorines here and chlorines there and there. And it's, would that give us a dipole? If we did this. If we put these here, like that, put chlorine here, chlorine here, chlorine there, chlorine there, then chlorine's going to be more electronegative, like that, like this. That possibly could be nonpolar. That puts these 90 degrees, these 180. Yeah, I don't see why not. But when you take the test, here's the best answer. Put your lone pairs at the apex. And your chlorines around that. And that gives you that gives you a nonpolar. Actually, to answer, let's see, B, give the shape of the molecule, square planar. Now, I can only speculate that this has been confirmed by other means, square planar, which would then put these lone pairs at the either apex of that octahedron. And then, of course, either choice that we had here would still make the molecule nonpolar. Either one of those choices would do that. Okay. So we can do anything else now. I just wanted to be sure and get those in.
How about 34?
34. Okay. Of the following, which molecule has the largest bond angle? A. Ozone. We drew ozone before, didn't we? So it's going to be linear no matter which one we choose. Right. So 2, 4, 6, 8, 2, 4, 6, 8. So the bond angle is going to be whatever is across this central atom, because that's the only one that's central. These two guys are not central. So it's 1, 2, 3 groups, which means trigonal planar, right? So it really is going to look like this, that, and that. So the molecule is bent. And our starting position here would be, let's see, there. Our starting position here would be 60 degrees, right? Because, is that right? Well, 120, excuse me. Yeah, 360 around. So it's 120, 120, 120. So 120 would be ideal, but with this lone pair, you know how lone pairs do, they balloon out. So they're going to shrink this down to somewhere around maybe 110. Or maybe a little more, something like that. So how about B? We have 2. Okay, so we got 6 here, and we got 2 times 7 is 14 here, so we have 20 electrons. Got oxygen in the middle, fluorine, 2, 4, 16. Okay, so 2, 4, 6, 8, 10, 12. Which would be 4. That. Okay. Octets are satisfied. So what does 4 here give you? Electronic tetrahedron. But these 2 lone pairs would make this a bent molecule. Kind of like water. Right? The starting position for this bond would be, for tetrahedron, 108.5. But these 2 lone pairs would shrink it down. It's probably maybe 104, something like that. So this one is a smaller angle than that one is. So far, A wins. Let's see what C has to say. HCN. What's that if it's a gas? Hydrogen cyanide. What if it's dissolved in water? Hydrocyanic acid. Just checking. Okay, so we're going to draw the structure. So this is 1 plus 4 is 5, plus 5 is 10. Okay. So we have like that, 2, 4, 6. So we have 2, 4, 6. We don't have to worry about hydrogen, it's happy. So what we're going to have to do is, to satisfy the octet on carbon, is move 2 of these. that. That's a linear molecule. 180 degrees. So at this point, C wins. And then water. We've done water before. It's kind of like this one. So it starts out at 108.5 and shrinks down. So C wins. 180 degrees is the largest thing. E would only be true in this case if there were another linear in there. But there's not. Just that one. So C wins. How about all these others asking for shapes? Any trouble with those? Okay, that's good. It looks like they're asking for molecular structure. Structure, molecule. Okay. So you have to go through electronic structure to decide what the molecular structure is. Are we good? Okay. Take a short break and reconvene in the lab. Let's see, let's stop this thing.